Welcome everybody. So this is a bonus lecture and one of many bonus lectures that we're going to have. This is the first bonus lecture. So I'm going to kind of explain what's going on here. So if you've already taken the class and gone through all of the lectures, then you're going to have a really good idea of how to design electronics, build printed circuit boards, etc. So the bonus lectures are going to be kind of a potpourri, just random things. It might be something that one of you suggested that you wanted to learn about in a single lecture. It might be something cool that I want to show you in a single lecture. And it might be something not completely related to electronics. It may be something more compute related or microcontroller related, something higher, maybe retro computing or gaming, something like that. And then we'll learn about something, tear something apart, do something, build something, but we'll try and keep these in one lecture. So anyway, I've got many ideas, a big long list, and there's no real order how I'm going to do this. But the first one, what I thought, I was just sitting here and I just finished a medical product a while ago. And one of the things that we need to do in this medical product was sense force. And there's lots of different kinds of force sensors, but many of them are very expensive and many of them are very large. So we had to kind of find something that was very small, and there are a number of manufacturers that make what are called force sensing resistors. And if you take a look on the screen here, one of these companies is called Interlink Electronics, and you can see some of their products here. And so what these things are, basically they are a laminated series of materials that when you press on it, it changes its resistance. And so there's a certain construction to these, and we're going to take a look at them in a second. But you can see there's these different sizes, and this one right here is maybe the size of a dime. This one right here is maybe the size of a quarter. And then it's really simple. It's basically a resistor that as you squeeze and press on it and apply a force, the resistance changes. And then we can take that value of resistance and put it into a circuit, an analog to digital converter, or an op-amp, something like that, and control something directly. Who knows? The whole thing is they're super cool, they're relatively cheap, and it's a fun sensor to be able to play with. Now, so what I'm thinking is, let's take one of these sensors, which I have over here on the bench. Let's build a basic circuit with the sensor with an op-amp. And in the course, we didn't really talk about op-amps, so I'm going to briefly talk about it. But op-amps are a massive subject. In fact, in college, if you get an EE degree, op-amps are usually 1 semester, sometimes they're 2 semesters. So when I took EE, it was actually 2 semesters, beginning and advanced op-amp design. So a whole year just to learn op-amps and everything that they do. So obviously we can't learn op-amps in a 30 to 60 minute lecture. But I'm going to kind of give you a quick and dirty overview of what they do, and then we're going to use it in the circuit. All right, so we're going to need a force sensing resistor sensor, which I have many of them. We're going to need an op-amp, and we're going to just build up a little circuit. We're going to basically convert force into a voltage, and then we're going to plot it on an oscilloscope, and then we're going to maybe we could use it to control an LED, and then maybe talk about some other things we could do with it. Maybe use a comparator, an analog comparator, and compare the voltage of something, and when the force exceeds something, it could turn something on, something like that. So we'll talk about that, and we'll see what we're going to build. So before we get into all that, let's do our homework. All right, so the first thing is I wanted to show you this website, Interlink Electronics. And like I said, there are a couple companies that make these sensors. So let's take a look here. Here's another company. This one's called Techscan. And this company makes some of the smallest sensors I've ever seen. And again, you can see here 3.81 millimeters, 9 millimeters, 9 millimeters. So this diameter of this little sensor is, about 4 millimeters. That's pretty small. All right. And then they have these kind of mechanical little protrusions or contacts that you have to mechanically connect to. Usually you don't want to solder to these because you'll melt the plastic here. All right. So Techscan and then the other company, Interlink Electronics. The technologies are very similar, so we're just going to kind of look at these. The Techscan parts are very expensive, actually. So unless you need something really small and Interlink doesn't have it, I would just avoid the Techscan at first because they are expensive. Unless you can probably find them on eBay. Someone's bought 1,000 of them or something. All right, so let's go ahead and let's take a look here. So depending on what you're doing, you might need something the size of a quarter, and then you might need long leads or short leads, long leads or something the size of a dime. So they have these variations of it so that you can kind of use what you need for whatever it is you're building, and you don't have to fabricate too much. All right. Now what I have, I believe, over here is I have the FSR 400 and I have the FSR I believe I have the short also. So the FSR 400 is what I have over here, which kind of has this smaller sensing pad. All right, so let's just click on that. All right, and then you can kind of read about it. And now they make these sensors with different sensing capabilities. So their range is different. So some of them can sense a larger range or a higher amount of force, and some of them are for a lower amount of force. So you kind of have to read and figure out what you want and order what you want exactly. All right, now the other thing is when we're talking about, so let's back up here. So if it's been a while since you've done, high school physics or whatever, so these are measured in newtons. How much force you can apply is measured in newtons, right? And you apply this force over the surface area of this little sensor. So 0.1 newton, so force is as low as 0.1 newton and a sensitivity range of 20 newtons. Now, for example, if you're in the United States, most people don't know what a newton is. They've heard it before, but unless you're an engineering student or something, you're not going to be familiar with these. So the one thing is just being able to convert these to get an idea. So I think I have, let's see, a Google, yeah. So we look at a newton here. So 1 newton is about 0.22 pounds of force, right? Or another way, if we say 1 pound of force is about 4.44 newtons. So that kind of gives you an idea. So 1 pound is about 4.44 newtons, all right? And again, 1 newton is about 0.22 pounds. So that kind of gives you an idea. So in the case of that other sensor, it just said that it can measure from 0.1 newtons and a sensitivity up to 20 newtons. So 0.1 to 20. So let's take a look at that. So 0.1, all right, so that's, 0.02 pounds, right, and up to 20 newtons, right? That's 4.4 pounds, about 4.5 pounds. So that's a good amount of force. Now, you're going to be applying this force with your typically, maybe it's a sensor you're going to press on it with a finger or something like that, or it could be you could have a mechanism, a mechanical mechanism, where you have maybe an actuator and the actuator is pushing down on the sensor, something like that, right? So anyway, if it's something you're going to press with your hands, believe me, 2 or 3 pounds of force is quite a bit for your fingers to be pushing down, or 5 pounds is quite a bit, so that'll suffice. But if you need something that can measure a higher amount of force, you can still use these, but you can adjust the electronics and the sensing so that you can kind of get a larger scale, all right? So anyway, so that's that. Now, on the Interlink page itself, there's a data sheet, integration guide, and a bunch of other things here. Unfortunately, they make you kind of fill things out. So if you want the integration guide, you got to fill this out and, put your name and all that just to get the information. However, on a couple different websites, I was able to find this SparkFun for one of them. So SparkFun has the same product and it's for sale here, and this is exactly what we're looking for. And you can see here there's kind of a size, and so like I said, this one's very small. It's like the size of a dime, and then the bigger one's about the size of a quarter. All right, now if we go ahead and crack open a couple things, we can get the data sheet here. So again, showing the diameter. So this one's 5 millimeters, and this one's 13, and so on, depending on what you want. So this would, for example, this large 38 millimeter square one, maybe you want to sense when a vehicle drives over something, a bicycle, a car, whatever. You could put an array of these, or you could put one, and you could put a pressure plate, and then you could sense what's going on there. All right, and then it shows various different parameters and so forth, and then application information. So this is kind of this is one of the things I wanted to show you. In addition, there's what's called if we go here, there's what's called an integration guide. And I want you to read that as well. You're going to download that and read that if I can find it. Yeah. So here's a force sensing integration guide. And what this is, it's 26 pages. This is kind of a quick and dirty explanation of how this technology works, right? So, I've read it, you should read it cover to cover so you know. And then it kind of talks how this thing works. So it's got kind of this flexible substrate here, which is this, kind of plastic polymer material. And then it's got this little spacer here. Now the spacer is just mils thick, so there's open air here. Then there's this resistor here, and then the whole idea is as you press down on this, you start making contact and shorting these little resistive elements together. And as you do that, the resistance changes, and then the signal is sensed with these two conductors here. It's as simple as that. Except it's made the construction is very, very accurate and precise and repeatable, so these sensors work very well. So these sensors actually work very, very well. Now, one of the problems with them, let me see if there's a chart here, is, yeah, so you can see here the chart. So we've got this conductance here, right? And conductance is the opposite of resistance. So here's resistance here. And you can see clearly this is nonlinear, right? So this is a curved chart here. And now it's linear in small pieces, right? So if you want to sense from here to here, it's linear, here to here, it's linear, here to here, it's linear. But if you want to go all the way from here to here, it's nonlinear. But this is no big deal. So what you do is you simply build your sensor, and then you basically apply a force, a known force, 1 Newton, 2 Newton, 3 Newton, 4 Newton, 5 Newton, etc., up to 20 Newtons or 100 Newtons. You measure the final voltage out of your system, right? We put that in a table, and then we use a curve fitting algorithms, or like a least squared algorithm, and then we could figure out what the force is very accurately, because we can basically, this is clearly a second order curve, third order at most, but a second order curve would fit through here nicely. It's clearly parabolic. And that way we could use a lookup table to figure out what the force is very, very accurately. All right, so don't worry about the nonlinearity. If it's too non-linear for you, then you're just going to use a microcontroller. You'll, through experimentation, run the system, put a Newton of force, 2, 3, 4, 5, etc. Then you will measure with a third-party measuring device. So you're going to need something to measure force, so you know what force you're actually applying. You're going to correlate that with the voltage, create a table, or the resistance, create a table, and then you can use that lookup table to figure out, so I've applied, so I'm reading whatever the voltage is. Now, of course, this is conductance and resistance, which is going to result in a voltage, because we're going to basically create an amplifier, and we'll have a voltage, and then we'll know what the force is to each one of these things, right? Whatever the gram force is or the Newton force is, right? Okay, so that is that. And let me see, is there anything else here I wanted to show you? Yeah, and this is just, so again, do's and don'ts, how to mess with this stuff, be careful of it. And when we go on the bench, I'm going to show you how I fabricated some of these things to connect to them. They're mechanical, so you can't be soldering to them, you'll melt them. So you've got to kind of use mechanical connectors, right? And then it's got some suggested interfaces for basic sensing. So we see this symbol right here, and this is an OpAmp, or operational amplifier. And I've probably mentioned this in the course if you've already been through the entire course, or you've probably heard this word before. An operational amplifier is a kind of an idealized amplifier. And inside of this little triangle are many dozens, if not hundreds, of components to try and create this perfect amplifier. Now, of course, nothing is perfect, but it's perfect within reason. So basically what an op-amp allows us to do is things like amplification, filtering, mathematical operations, addition, subtraction, multiplication, logarithms, all crazy, crazy stuff. Op-amps are crazy. And like I said, it's basically a semester or good year course to dig into op-amps. Now, there are hundreds, if not thousands, of books on op-amps. I'm going to show you a couple. But an op-amp is an amplifier. And in this case right here, what's going on is the force sensing resistor is here. It's being used as a variable resistor. Then we've got a fixed resistor here. So we've got a voltage divider going on here. Then this op-amp is just being used as a simple non-inverting buffer. That's all it's doing. It's buffering it. So basically, we want to sense the voltage at the node, but we don't want any current to be drawn out of here, because as we draw current out of here, we would change the resistance, and the system would change and be inaccurate. So that's another property of op-amps. Ideally, no current flows into these or flows out of these two terminals, called the non-inverting and inverting terminal. And we're going to take a look at this just real quick. I'm going to kind of give you a crash course in op-amps just for a few minutes to kind of get your feet wet in it. But anyway, we can use the properties of op-amps to create this, basically it's a buffer, and it's an analog buffer. So whatever voltage is here, we're going to see here, but when we sense this voltage, the system basically will draw no current from it magically. But on the output here, we can actually drive a lot of current. So for example, this output is going to follow this input here. So we're going to be able to track what this force sensing resistor is doing. And then say the voltage is 1 volt, 2 volt, 3 volts, and I want to pull like 30, 40, 50 milliamps out of here. Depending on the op amp, I can do that, and it will have zero effect on the circuit. Because it has zero effect on this, it won't change the voltage and thus change the reading. So remember, when you're doing sensing, ideally when you're talking to your sensors, you don't want to modify or disrupt the sensor itself as you're sensing from it, right? You want to basically look at it without it knowing you're looking at it. Okay, so this is one possible configuration here. And then it's showing you that V out equals V plus, whatever this V plus is here, divided by 1 plus, RFSR, which is this right here, and divided by RM. So that's the equation that you would get. So that would tell you what the V out would be. All right, and it's just saying some op amps that you can use to try out. All right, and then here's another one, so adjustable buffers. So again, it's going to show you a bunch of different designs, all based on op amps here, and this gives you different offsets and different things. So you can read through all this to kind of figure this out. What we're going to start with is just this one right here. We're just going to basically use this as a voltage divider. We're going to basically get an output of it. And we're going to use that output to drive an oscilloscope and maybe something else so you can kind of see this thing working. All right, but again, I'd like you to read all this so you can kind of get an idea here. And then, of course, you're going to be, and then showing some other, cool ideas here. Like driving a relay, for example. So when this thing, so here, threshold relay switch. So when this op amp, when the output hits a certain voltage, it's basically going to turn this thing on, and this relay is going to turn on. That was just what I was saying, using a certain force to turn something on, right? So anyway, read some of this, and then there are these kind of samples here. So if you have a 1.5K or 4.7 or 7.5K, it's going to kind of give you an idea of the different forces you could apply, right? And remember, 1 kilogram is 1 Newton. These different forces you could apply, and then what these curves are looking like with these circuits. So if you use this feedback resistor of 7.5, 4.7, or 1.5 in a simple circuit, these are the kind of curves you're going to get. So for example, you see here, if you use this 1.5K resistor, we get this initial nonlinearity, and then this thing settles into this nice line, right? And then we can basically read from 200 to 1,000, but the voltage doesn't change much. Now, if we go ahead and we use like this red resistor, which is a 4.7K, now what happens is, again, we get this nonlinearity, and it happens a little bit longer maybe, right? A little bit longer. Then it's linear, but now we get kind of from 1.5 to 5 volts. We get more of a dynamic range. So it's a give and a take, right? So it's either you get more dynamic range, you get more nonlinearity, or you get linearity, less dynamic range, etc. So you play with this stuff and just figure out what you want to do, okay? All right, so that's that. So that's the force sensing resistor. We're going to use one from Interlink, and let's see here. I believe, yeah. So this is basically what we're using, and let's make this a little bit bigger for you guys. So this is a DigiKey right here, and I've kind of looked this up, the FSR 400 series, right? And the FSR 400, if we back up here, is this series of the small one and the big one, right? And let's go back here. So you can just order these right now. And again, these things are not cheap. $7, $8. These things are not at 1,000. They're $385. This is not a cheap little device. So, but if you want to sense force accurately, this is a way to do it. Now, other force sensors, really complicated, advanced ones, could be 100, 200, 300. They're $1,000, $10,000 force sensors actually. So if you want absolute accuracy, but these are usually good enough for the kind of applications we're going to be doing in sensing if something's coming, going, robotics, etc. All right. So you can order a few of these. Now, they are expensive, so what I do suggest is maybe look on Amazon.com or maybe look on eBay, whatever, and see if you can, Alibaba, Banggood, see if you can find some of these things cheaper, maybe a bundle of 10 or something on eBay for $5 if you want to play with them, because they break pretty easily. And let me go back to that SparkFun. So you see right here this connection. So these things are basically crimped. These are little crimps here, and they're just crimped. Can I make this bigger? Just crimped on here. And if you apply any force, it just snaps off. So the first thing that I do when I want to play with one of these is I put a couple little connectors on here, and we've seen that stuff before, and I fabricate a little cable, and then I put some heat shrinking around this to protect it and give it some strain relief, so as I bend it around and stuff, it doesn't break. All right, so that's kind of how you have to work with these things, and you will break them as you play with them. All right, so we've seen the data sheet here. So here's the FS400 data sheet. So you're going to download that from Interlink Electronics, which if we go back to the website here, is just interlinkelectronics.com. And then the other thing that we are interested in is this guy right here, which is this integration guide, force sensing resistor integration guide and evaluation parts catalog. So you can get this from Interlink, or you can just get it on SparkFun very easily. All right. And then, okay, now let's go and let's talk about, so what we're going to do is we're going to build a circuit. What circuit are we going to build? We're going to basically build this circuit right here. And let me find that again. It should be right about here. Down a little bit. And here we go. So we're just going to build, something like this. Very simple circuit right here. And as a matter of fact, I think if I go, there's even a simpler one. Here's one here, and yeah, there might have been another one. Let me see here. Let me scroll through here. There's kind of a couple good ones to start with. All right, so here we go. And basically it's just a variable resistor, and we're just going to put it through an op-amp, and we're going to use an op-amp as an amplifier, which we haven't learned in the course how op-amps work, but I'm going to show you real briefly. And let me see if there's, no, not really. There's another circuit that I like. Another circuit that I like here, but it's not in here, I don't think. Yeah, and these are current to voltage converters. That's why there's this feedback resistor and there's no more voltage divider. That would be hard for you to even see though if you're not familiar with op amps. All right, so anyway, we're going to build the first simple circuit, which will go back to any of these, and it just looks like this. We're basically just an op amp, resistor, and our force sensing resistor, and that's it. Okay, now let's switch gears to op amps. All right, so let's talk about op amps. So operational amplifiers. So where do we even begin with that? All right, so the first thing is there are about 1 billion operational amplifiers. Inside of each operational amplifier is many dozens of components that create kind of this virtual amplifier. Now, what I'd like you to do is, again, always lots of homework with me. You know that if you've taken the class already. All right, so there's a couple books that are easily available online. One of them is called the Handbook of Operational Amplifier Applications, and it's written by Texas Instruments, which of course make operational amplifiers. So I want you just to search for this, and then just, it's SBOAO092B.pdf. If you just search for that, you can probably find it. But anyway, Handbook of Operational Amplifier Applications. It's 100 pages. I would just like you to read it. All right, and it's going to start to show you how these things work, what they look like, what their models are, and so forth. So this is one example, one good book. There's another book, and let me see if I can find it here. I think I already downloaded it as well. And let me see. This one. Again, another Texas Instruments book for free. Op Amps for Everyone by Ron Mancini is the editor-in-chief. So I believe this is like and there's different versions of this. Yeah, 2002. So this is very new. So as far as op amps go, this is brand new, right? It's like transistors. This stuff changes, but what we're going to be using, this is, as far as we're concerned, state of the art. Okay, so I want to kind of use op amps for everyone as our reference. Now, let's go through here. And what I want to do is I want to show you kind of the model of an op amp and just a couple circuits. All right, and then again, you're going to have to read this. Because this subject is very, very large, and then this is kind of circuit review, which you would have already learned in the class, but what we want is section 3 or chapter 3, I believe, yeah, is the development of the ideal op-amp equations. All right, so you read this right here, and what it's going to talk about is an op-amp is this ideal amplifier, and it was designed and architected to have certain properties. Now, nothing is ever ideal, so it's close to ideal, as long as you use it in a certain domain and you don't exceed that domain, right? As long as you play by the rules, it will act like this ideal amplifier for all intent purposes. It'll be perfect. If you break the rules, it will not work anymore. All right. So what I want you to look at here is kind of this model of an ideal operational amplifier. And so let's look at what's going on here. So it says things like we've got IB equals 0. We've got IB equals 0. So this current going in this direction and this current going in this direction are both 0. Then it's saying the voltage across these two terminals, VE, is also 0. Okay. Then it's saying its input impedance, ZI, is infinity. It says infinite input impedance. All right, great. And now what's going on here is basically this is an amplifier, right? And it's going to amplify. And so now we see this output, this A, so it can actually source infinite current. All right, so it's infinite current supply. And here's another, I wish this was true. The output impedance is 0. So it has 0 output impedance, it can source infinite current, it has infinite input impedance, and it draws no current. So basically this thing is completely ideal. So if you look up here, it kind of talks about all these things, right? Now in reality, these things aren't going to be true. So maybe it can output an amp or 100 milliamps. Maybe its output impedance is 10 ohms or 50 ohms. Maybe its input impedance is 100K or a megohm or 10 megohms. Maybe the input currents, these input currents that come in here are maybe microamps or picoamps. And maybe this voltage difference between the minus, which is called the inverting, and the positive non-inverting terminals, maybe the differential voltage is millivolts or nanovolts, maybe picovolts. I think there's some picovolt ones, operational amplifiers. Okay, so anyway, that's what we're looking for. And here's the rule. The more ideal the device, the more expensive it costs. So if you're building, for example, military grade, medical grade hardware that's dealing with very small signals, and noise is very important, where basically you're going to deal with very tiny little voltages, and you have to have these things operate so that there's no noise and all that. You're going to be using very expensive op amps, and by very expensive I mean you could spend a transistor's a penny, 2 pennies, 5 pennies. An op amp could be 20 bucks, 50 bucks. I never like to say never, but I've never seen an op amp that's $1,000, but I bet you there is one. But there's op amps that are tens of dollars easily. So we're going to use op amps that are $1, $2, $3, 50 cents, right? With certain properties, okay? So that's what we're going to pick. Now, picking op amps is like picking transistors and field effect transistors. There are just too many of them. So what you do is you have to pick a company that you like, a TI, a Fairchild, a this, or that, whatever, and kind of, get the part from them, whatever the company is that you like. And otherwise, you'll just be overwhelmed. So I'm going to just pick one for you, and then we're going to build something with it. All right. Now, all right, so that's kind of the model of the op amp. And then what happens here is it's going to start showing these different circuits. All right, so let's go ahead and let's take a look at some of these circuits. All right, so when you start off with op amps, you're going to probably be building 2 circuits a lot. One is called the non-inverting amplifier, and one's called the inverting amplifier. The non-inverting amplifier is nice because it doesn't invert anything. In other words, if you put a voltage in, say V, you get something times that voltage V out. The inverting version, you get minus V out, right? So it inverts the signal somehow times some gain or some other transfer function. All right, so let's just take a look at this. And now, again, you're going to have to read through this because it's going to derive the equations. All right, it's going to derive what's going on here. All right, but in a nutshell, and here's another thing. So now, when you want to derive the equation of an op amp, you can actually do it, and it's actually kind of fun. It's a fun exercise, and of course, if you take an EE course in this, you'll derive all of these yourself. You're not going to be given them, you're going to have to derive them and figure it out. But how do we derive it? Well, we derive it based on the laws of the op amp. So we assume that the guy who made the op amp, or girl, created this idealized version of it. So we know that the gain is infinite. We know that the output impedance is 0. We know that the input impedance is infinite. We know that the current into the inverting and non-inverting terminals is 0, and so on and so forth. We have all these rules. So then what we can do is we basically can put components on the op-amp, and then using nodal analysis or mesh analysis, whatever you want to do, circuit analysis, we can constrain the circuit such that we can start to write formulas or a set of equations, and out of those sets of equations will emerge or pop out the transfer function for the op-amp. And if you put capacitors and inductors and you have the proper formulas for them, you can get very complex filters and all kinds of cool things. Anyway, in this case, he's just starting off very simply, and he's saying, all right, we've got two resistors here. One's I'm going to call RF for feedback, and the other one I'm going to call RG, I assume, for it's going to ground. So the idea is we're going to have a voltage here, and the voltage is just going to be on this single input, Vin. All right, and that's all we know. We got V in, we got V out, we got these two resistors. My question to you, his question to us, and all that is, what is V out? What's V out? Well, he goes through this explanation here, kind of explaining why it's like that. And then he comes down, and he says, hey, here's the deal. V out over Vn equals 1 plus Rf over Rg. So 1 plus Rf over Rg. That means that V out, so if we take V in and move it over here, V out equals the input times this. So that's the transfer function right there. So basically, it's going to have a gain of at least 1 plus the ratio of these two resistors. So for example, say if you wanted to have a gain of 1, then we would make this feedback resistor 0. So if we make this feedback resistor 0, right, then basically it's going to have a gain of 1. Then if we make this RG infinite, we could make it infinite, right? It wouldn't notice it. Then we would still have this gain of 1. So basically, if you just tie the output to the input, you create this non-inverting amplifier that just the input follows the output because the gain is 1. All right. If you leave these resistors in here, then the gain is whatever this is. So for example, say we put RF as 100K. Then say we put RG as 1K. So 100 over 1 is 100, plus 1 is 101. So the amplification would be 101 times the input voltage. Now wait a minute, you say, wait a minute, what if I put 5 volts in here? So you're telling me I'm going to get 505 volts out of here? No, of course not, because that would break all the laws of physics. You can't get something you don't have. But within the, so say that the op-amp is powered. Now we have to power these things. It's an active device, all right? We're going to power it, which is not shown here, with a positive and a negative supply. So say the positive supply was 10 volts and the negative supply was minus 10 volts. So when we tried to do this amplification, so we said the amplifier is going to amplify 101 times. Let's call it 100, all right? 100 times. So if we put in a little voltage, say 0.1 volts, right? 0.1 volts times 100, right, would be 10 volts. So it would take the 0.1 and we would get 10 out. But the moment we put 0.2 volts in, right, that would be 20 volts out, it's still going to stay at 10 volts. It's not going to generate some miraculous voltage. So again, the op-amp will only operate within, the realms of reality, but it will attempt to be ideal. It will attempt to do these things, all right? So it's never going to generate more voltage than you give it for the rails, for the power supply rails, which we're going to see where you hook that up. And again, it's never going to give you more current than the data sheet says that it can give. So even though you try to pull more current out of it, it's just not going to give it. If its op-amp is rated for 100 milliamps and you put a load on it of 1 ohm, right? And so we put, say for example, we put out 10 volts and we put 1 ohm, right? So we got 10 volts, we got 1 ohm, so that's 10 amps. No, 10 amps is not going to come out of the, is not going to be sourced by the op-amp unless it can source 10 amps. It's probably going to put out 50, 100, 20 milliamperes, whatever it's designed to do. So you can't break the rules, but as long as you stay within the rules and usually stay away from the barriers, away from the envelope. So you don't want to use this thing all the way to the envelope because then it's going to start to act nonlinear. So in other words, if you know that the op-amp has a and we're going to talk about some other things. Say we know that the op-amp it can source 500 milliamps. I'm probably not going to push more than 300 or 400 out of it. I'm surely not going to take it all the way to 500 because it's probably going to start acting weird, right? So if I want 500, I'm going to get an op-amp that puts out an amp, right? Remember, always over-design everything so that when things go sideways or things happen that you don't anticipate, nothing breaks. Okay, so this is the non-inverting amplifier. And we see the equation right here. It's V out over Vn equals 1 plus R feedback over Rg. And these resistors will typically be called R1 and R2 in a lot of other books, R2, R1, right? And then what I just said when I was just kind of saying, if RG becomes very, very large, right, and or RF becomes very, very small, right, then this whole thing reduces to V out equals 1, right? All right, times Vn if Vn is 1. Okay. Okay, so let's keep looking here. Now, the inverting op-amp. So this is kind of what you're going to see more often. And the reason why is because this is a little bit more, having the 1 plus term is kind of a little unsettling as an electrical engineer. I don't like the 1 plus because it's 1 plus something. And that something is never ever really going to be 0. It's 1 plus it. So we kind of like no 1 plus. We just like input voltage times something, done. This is what this does. Now take a look here. So V out over V in equals minus RF over RG. Now look at the architecture of this one. This one has the feedback resistor going back from the output back to the input. And here's another little comment is op amps they operate with feedback. If they didn't, they would just be open loop and they would just they would saturate, they would go crazy. So we take some of the output and we feed it back to the input and create this feedback loop, and that makes them well behaved, all right? Anyway, so we take this output, we feed it back here through the feedback resistor, then again we have this G, which is not our ground, it's just RG, which I'm sure it says what he likes to call RG. But anyway, typically this would be R2 and R1, right? R or RF and R1 or Rn, right? Anyway, either way, he goes through the rules of the op-amp, and then he drives what this equation has to be. It just has to be. And then it's V out equals V in times minus RF over RG. So what is this thing doing? It's inverting the minus sign. And what's the amplification factor? It's RF over RG. Super simple. So let's say we wanted to make an amplifier that multiplied the input voltage by -1. That's all I wanted to do, by -1. All right, that's it. So I'm going to make RF and RG the same. Now, also there are rules for RFs and RGs. You don't want to make them too big or too small. So make them usually in K, right? So don't make them 1 ohm and 2 ohm. Make them in K. Don't make them in hundreds of K usually. Make them in tens of K. Make them in K. So I'm going to probably make RF and RG both 10K. All right, 10K over 10K is 1. So V out over Vn equals -1. Boom. So my output voltage will be my input voltage inverted. Now, wait a minute. This is cool. So I can put in a positive voltage and get out of negative voltage, but my power supply is only positive. No, you can't, unless you have a negative power supply. So to get the inverting op-amp to work, when we power this thing, we're going to put a plus V and a minus V on it, a plus 5 volts and a minus 5 volts, a plus 12 volts and a minus 12 volts. So whatever we force it to do, it will do if it can do it. So if you don't have a negative power supply on here, you're not going to get a negative voltage out of it. You'll get the closest to negative that you can, which is 0. So again, you can't violate the laws of the op-amp, and you can't violate whatever you have in your circuit. It's not going to work. But if you don't violate it, it will work. So for example, if we had a plus and a minus 12 volt supply, and we put in 1 volt, we'd get out -1 volt. If we put in 5 volts, we get out -5 volts, et cetera, et cetera. So we just basically did mathematical inversion, right? And if you wanted to gain it a little bit, say we wanted to multiply, so say we wanted to multiply the input by the output by -2. Then I would make RF 20K, and I'd make RG 10K. So now my gain is 2, and with the minus sign is -2. Done. So I just made an amplifier, and it multiplies by 2, but what kind of 2? A -2. It's an inverting amplifier. Okay? All right. So that's that. So that's my quick and dirty op-amp introduction here. And we're about 40 minutes in here, so I want to finish the rest of the time and kind of do some circuitry here. But this is going to be painful, but I want you to read this whole book and at least skim it. So the first few chapters are 1, 2, 3, 4 are understandable. Then after that, it gets fairly advanced. But just eyeball it for me, all right? Unless you're comfortable with the mathematics and so forth. But you'll see a lot of really interesting things in here, all right? But the first few chapters are doable. Okay, now, all right. So let's find an op-amp. All right. So let's find an op-amp. So I like to use many op-amps, but one that I prefer is, let's see where it went. Let's go back here. It's called the LMV 796. All right. And again, I could spend many lectures just explaining what all the parameters of an op-amp do and what they mean. But I'll tell you right now, this, and you can see this is not a cheap op-amp. It's $1.50. It's not cheap, right? And at 500, it's 88 cents. So it's, it's a dollar op-amp at 100, right? It's not cheap, which means it's pretty good, and it's going to do a lot for you, and it'll get what you need done. Now, let's again, I hate just showing you stuff without kind of telling some of the things. All right, so first it's a general purpose op-amp. That means it's not been optimized for some special application, maybe high speed, maybe low noise, maybe 100 other things, all right? It's just general purpose. Okay, next it says how many circuits. Well, there's just one op-amp per package. Many times there's many op-amps per package just because it's convenient, but also so they're thermally related to each other. If they're in the same package, as the temperature of one changes, the temperature of the other one changes. So if you're using these op-amps to amplify or do some signal processing, you want to make them all thermally the same, and that's why they're in the same package. So that's what's important. You want to have, so if you want two op-amps, don't put one op-amp in one package and another op-amp in another package. Put them in the same package if you care that they're thermally connected. All right. Next, slew rate. What is this? All right. So the slew rate, what this is, it says slew is the rate of change. So the slew rate is 11.5 volts per microsecond. Let's take a quick look at that. I just want to graphically show you that. All right, so what this is talking about here is this. So let's get on our little graph here. All right, so this is time down here, and this is voltage here. All right, and so what this is saying is that, and let's put some little tick marks here. All right, and if we go back, this is saying it's 11.5 volts per microsecond. All right, so if each one of these was 1 microsecond, so 1 microsecond, there's 2 microseconds, 3 microseconds, 4 microseconds, 5, 6, 7, 8, etc., right? And then up here, let's put some voltages. Let's say that this is 10 volts, 20 volts, 30 volts, 40 volts, etc. What this is saying is this. It is saying, and let's pick this color, every 11.5, every microsecond, it can go from basically where it was 11.5 volts higher. So it can go from 0 to 11.5 volts in 1 microsecond. So here's 1 microsecond. So in 1 microsecond, it can go to about here. All right, that color's no good. Let's use yellow. That's better. So it can go like this. So here is the slew rate. So this is the slew rate. What this means is, this is how fast this op-amp can adjust to signals. So if you're forcing the op-amp for really high gain and high amplification and really fast changing signals, it may not be able to keep up if it can't maintain, if it's over the slew rate, right? It's not going to be able to keep up with the signal. So if the op-amp is, say, getting a signal on the input that's going at 100 megahertz and the voltage is changing radically, it's going from 100 volts to 0 volts. If you take those two things together, the slew rate is going to be way too fast for this thing to keep up. So you have to make sure that whatever happens, whatever signal you're trying to amplify or process, it will be within this slew rate or within this rate of change that this particular op-amp is capable of doing. Okay, that's what slew rate is, and that's what it is related to op-amps. Now, what's this other thing? Gain bandwidth product, GPB, GBP. So what this is, it's the gain times the bandwidth. All right, so what that means is this. If you want to amplify a signal by, say, just a factor of 1, then that means the highest signal that you can process is 17 megahertz. Now, if you want to play with a signal that is 1 megahertz, right, 1 megahertz, then the highest you can amplify it is 17 times, because no matter what, the gain times the bandwidth can't exceed 17 megahertz. So that's called the gain bandwidth product. All right. Typically, we want these to be very, very high. Now, this op-amp would be nearly useless for a signal processing of very fast signals, of, say, radio signals or things like that. But for audio signals in the kilohertz range, it'll be more than fine. And that's what I typically use it for. All right. Now, what are these two things? input bias. What this is, remember the inverting and non-inverting inputs, the inverting and non-inverting inputs, right? Inverting and non-inverting, those two inputs right there. So what that has to do with is, and where did it go? That's how much current is pulled into those or pushed out of those inputs. Typically we want that to be 0, right? But it's 0.1 picoamps. That is practically 0 as far as I'm concerned. That is very, very small. It's a 0.1, it's a tenth of a trillionth of an amp, right? Very, very small. And then what is the input offset? 100 microvolts. Remember, that's the plus and the minus inputs. What is the differential voltage between the two? All right, that should be 0 ideally, but here it's 100 microvolts. Not bad, not bad, right? I'd like it to be down to 2 or 3 microvolts would make me really happy, but 100 is fine. Okay, and then current supply just means how much you need to supply to make this thing work. And then rail to rail means it can go all the way positive and all the way negative, right? So it's a rail to rail op amp. Some of them are single rail. They can only go to a plus to 0 to a positive voltage. So this is a really good op amps. Now let's look at the data sheet. All right. So here's the data sheet for the LMV 796 and 797. All right, you can kind of read through here. And then here is a kind of a little example use of it. And you can see you've got the inverting, got the non-inverting, got the output, got the input. Now, where is the power? Where does the power go? Let's take a look. So we go here, and here we go. So here is the SOT23 version, right? And you can see here's the output at pin 1. Pin 2 is V minus. You can't see that well. Uh-oh, end of the world. Let's rotate clockwise. You can't see that very well, but there it is. There's the V minus at pin 2, V plus at pin 5. The input plus is at pin 3, and the input minus at pin 4. Now, I'm going to tell you this. I want you to be really, really careful. I've done this about 1 billion times, all right? And I've blown something out. In my rush to build things, I look at the schematic and I see in plus and in minus, and I think that means the power supply in plus and in minus, right? And then I put power supply here, and then I put the signal here, and I blow the thing out. Be very careful. Always look at the plus and the minus. These are the inputs, and then the wires coming off kind of the sides of the triangular symbol, those are the power supplies. So pin 5 is V plus. We're going to hook that to 5 volts. Then we're going to hook V minus to 0 volts. We're not going to put it to a negative voltage because we don't need a negative voltage, because we're going to use this in the non-inverting configuration for our force sensing resistor. Okay, so what do we have? We have our LM796 here. We've got its 1, 2, 3, 4, 5 pins. I've already got it mounted on a surface mount board. All we have to do is kind of hook this circuit up. So what I'm going to do is I'm going to toggle back and forth between the drawing program here, and we're going to kind of draw what we're going to do. Okay, so let's go ahead and draw the circuit that we're going to build, all right? So we're going to have our op amp here, and then what I'm going to do is I'm going to draw the power supply. So this is going to be V plus here, and then this is going to be V minus here. This is going to go to plus 5 volts. Here is going to be our output. I'm going to take our output right here. All right, so I'm going to call this V out right here. Then we have our 2 inputs here. Here's one and here's the other. And then we will call this one, let's go ahead and we'll call this one the non-inverting and the inverting. Now let's go back and let's take a look at our pinouts here. So the positive V plus is 5 and the V minus is 2. So 5 and 2. So let's go put that in. So this is pin 5 and this is pin 2. The output, where's our output, is pin 1. And you know, be careful of this. And then non-inverting is right here, is pin 3. Pin 3. All right. And then the other one is pin 4. All right. Okay, so this is kind of what we want to build here. Now, we know, let's go back to our little FSR diagram here. And if we can find that circuit again, it's in a lot of different versions of these. Here it is right here. So it's very simple. We have our FSR here. And then what we want is to create a voltage divider, and we're just going to put that center node into the plus, and we're going to take the output and feed it right back to the input. So basically we're doing a non-inverting amplifier with gain 1. all right, as far as this is concerned. Then this resistor network is going to control what the output voltage is. Okay, so all we're going to do is copy this, all right, so very simple. Okay, so now what we're going to do here is we're going to take this output here, and we're going to, and as a matter of fact, yeah, we can do this with this color. So I'm going to take this like this, and I'm going to very carefully jump over that so you can see that. And that goes right there. Okay, and then here's our input. So this is where everything's going to happen. So now let's go ahead and let's use a different color here. Let's use green. So now what we're going to do is we're going to say plus 5 volts again, and then we're going to put our FSR in here. Now remember, this is not a potentiometer, so there's like different ways of drawing it. So see how they kind of draw it with this line through and this kind of thing here. We'll just use their convention. All right, this is our FSR. And then this is our resistor here, which sets kind of the gain here, or sets this kind of voltage divider ratio. And they call this thing RM. And I'm going to tell you right now, we're going to use either 10K or 100K in our examples. And if we look here, so here's 10K is the purple, it's this one. So with these forces right here from like 200 to 1,000 grams, we're getting these voltages from like 1 volt to 3 volts. But then if we put it up to 100K, now I want you to be careful here. This blue line starts all the way down here. It's just being occluded. So it starts all the way from 0 and it goes up to almost 5 volts here. So we get the whole range, but look, we have this really, really bad nonlinearity here. It's got to get up to about 200 before it turns linear. So we can either use it in this little tiny region here or use it over here, but this will give us the full range. So the 10K kind of gives us a good dynamic range, right? Kind of reasonable. It's from here to here-ish, that vertical range right there. And it's fairly linear this whole time. But the blue one gives us the whole range from 0 volts all the way up to 5 volts, but it's absolutely nonlinear. It's like, woo, this curve down here, right? And this curve right here is definitely not a second order curve. This is probably a third or fifth order curve to get this to fit here exactly, but at least a third order, maybe a fourth order to get good fit. But this one, this purple curve, that we can get away with a second order fit on that one right there if we want to use their lookup table and all that. But we're just going to put in 10K and 100K for these forces. And now, again, even though there's this table here, this table means nothing to us. We can't correlate this with anything. We have to actually measure things to create our own table to know what we're doing. All right. So this is what we're going to build. We're going to build this right here. We're going to build this exact circuit right here. So let's go ahead and go over to the bench, and we're going to just build this and then play with it. All right. So I'll meet you over at the bench. All right, everybody. So we're back here on the bench, and I've got everything kind of set up here. So here is one of these force sensing resistors. All right, right there. You can see that, and that's what it looks like. All right, and then of course I've created this cable. Let's zoom in just a little bit here. We'll zoom in just a teeny tiny sconce, which I've heard someone say before. There we go there. So there's our force sensing resistor. It looks exactly like we think, and then you can see I made this cable here and kind of connected all this together. Now, here are some that I got from DigiKey. All right, now these things, you saw how expensive these were, right? No joke. So check this out. So I ordered 3 of them from DigiKey. I ordered 3, and look, they gave me 3 bags, and in each bag there's like 25 of them. These things are like $7 each, right? So it's like hundreds of dollars of sensors right here. So anyway, this is what they look like. Let's go ahead and take one out here. This is the smaller one, the little shorter one, and I'm going to be very careful here. Camera. Okay, let's move this for now. There we go, and then I'll just pop one of these things out carefully, or not. Let me try this one. Nothing ever wants to cooperate. Okay, so it's getting caught. There we go. All right. Be very careful of these things. Kink these up. All right, so there it is there. So the whole idea is that when you make your cable for this, you're going to mechanically connect onto these 2 things, because if you try to solder, I guarantee this thing will melt. Now, what you can do is mechanically connect onto both these with a couple of little clips with wires on it, and that's what I did here, just same idea. Then what I did was I just really quickly did some soldering, solder, and then I went ahead and individually wrapped them in heat shrinking, and then the whole thing in heat shrinking. So that's pretty good, and I'm not going to bend this, but it's pretty strong in there. This is actually pretty strong. That's pretty strong. All right, but that's what it looked like, and then I had to make this out of it so that we have our little resistor here. Now remember, this thing is not polarized. It works in either direction. So anyway, no real difference. You can put it either way, but I would just come up with a convention so that, you know, from the top and call one side minus, call one side plus, and that way you kind of do things the same mechanically and electrically and all that. Okay, so let's move these things away over here and let's get our circuit down here. So as you can see, I've already built the circuit. And basically this mimics what we did. Now, if you've already taken the course, then there's a few things in here. So one, we've got our power coming in up here. So our power is going to come in here or come in here. And then I've got a bypass and filtering capacitor. I've got a 10 microfarad and a 0.1, and then I pop it over to the other rail here, 10 and 0.1. Of course, these are tantalum capacitors, and this is a ceramic capacitor, monolithic. So both of my rails are good to go. Then I've got my rails connected here, rails connected here. You can see these wires, because remember, they don't jump over with this particular board. This is open here, so you got to jump it over. All right, so here is our LM796 op amp. You can see it's pin 5, 1, 2, 3, 4, the way that this thing is worked out. And let me see if we can zoom in just a little bit more for you without losing focus. Yeah, okay. And now I've basically just mimicked that circuit. I've just mimicked the circuit. So here comes power. Now what's going on here? So I've got power, and then I've got my, this is a ferrite bead because I want it really, really quiet. And then I've got a capacitor to ground. Let's go back over to the screen, take a quick look at that. So back over here on the screen, one thing we kind of left out that I put in the design there was a couple added little features. And one of those is coming through here, there is a ferrite bead. So that's a ferrite bead, right? And that is for noise. So high frequency noise is going to get squashed by that. And then what else did I add? From the same node here, I put a capacitor, right, to ground, and this one is 0.1 microfarad. So this has a bypass capacitor, and it also can be used as a current source if this thing desires a lot of current, it'll have something to get it from. Now, on that topic, if this thing is going to be pulling a lot of current, maybe we want a 0.1 in parallel with a 10 microfarad so we can get some current so it doesn't have to run all the way back to the power supply, right? And remember, in the course, you're going to learn about that. If you haven't watched all the course, you're just skipping to here. We want to have both a capacitor for filtering, and we want to have one also for a local current source, okay? If we're going to be drawing a lot of current. All right, so anyway, those are those two additions. Now, another addition you're going to see over here is we basically need to put a load here. So when this thing's not doing anything, I just put, I think it's 100K just to ground. So we just put a 100K load here just so that this thing is just not kind of open loop, closed loop. We just put something to ground, and that's what we're going to put there. And then we're going to take this output and do whatever we want with it, all right? We're going to put it to a probe, the oscilloscope, that kind of thing, all right? So let's go back, and there would be the oscilloscope, and we just put a probe there, and then we would connect the grounds, and we'd be able to see the signal here. All right, let's go back. Okay, so we're back here. So basically, there's our filter. Filtering ferrite bead, which is basically an inductor. There's our little capacitor, little bypass capacitor. Then we've got our ground there. And then here's this is that RM resistor. Right now it's 100K. All right, that's 100K. And then this little capacitor right here, don't worry too much about this. This is for high frequency noise to go over the resistor. So it's a bypass over the resistor so that there's an AC path and then there's a DC path, and this is kind of an op-amp thing. Don't worry about that, but it'll work fine without it, but I like putting that on there. Again, that's a 0.1 right over that resistor. And then here's the output. And then you can see the output goes back to the input there. There's our output. There's that 100K I talked about, just to give it a load. And we're going to take the output here, and then there's ground right there, right? Okay, so I think that's it. So let's power this thing up and see what goes on here. All right, so I've got my handy dandy power cable. And again, if you haven't taken this course, I'm going to be saying a lot of things that are going to make no sense. You have no context, so you shouldn't be watching the bonus lectures, right? But if you so desire, then you can. Let's put this in here. And again, this is where mistakes are made. It's really easy, putting things in the wrong way and all that. So just be careful of stuff, put stuff in the right way. All right, so that's hooked up and good to go. Now what I want to do is I'm going to take our oscilloscope, which is on the other screen, which you can't see yet, and I am going to hook a probe up. And again, you know that dealing with the oscilloscope is just a nightmare. So we're going to hook the oscilloscope up here so these cables just get everywhere. All right, good. Okay, now we're missing one thing. What are we missing? We're missing the force sensing resistor. So the force sensing resistor, where does the force sensing resistor go? Back on the other screen there, which I'm not going to switch screens, it needs to go to the plus rail, so the +5 rail. So here's our input right here. So here's our input right here. And this is filtered, so I want to take the filtered one. And then it goes to that resistor. So it goes to the top node of that resistor. So it goes right there on pin 3, that non-inverting input. There it is. Okay, now what I'm going to do is I'm going to back this out a little. I'm going to zoom out here. So we're going to do this all simultaneously a little bit here. All right, and there we go. Okay, now I've got my force sensing resistor here. I've got my oscilloscope over there. All right, so ready? I'm going to push this. All right, and then now there's the oscilloscope, so you can see it. It's already kind of set, and the range is set. So we're going to push on this, and nothing happens. Why not? Anyone? We didn't turn the power on, right? So let's go turn the power on. All right, so you're going to hear it turn on. Okay, there goes the power. And let me get this back so you can see it. Sure enough, there it goes. So I am sensing force. Now the oscilloscope, because this is like a very slow DC signal, this oscilloscope does not like this. It likes fast signals and all that. So don't worry about it looking like it's hanging and glitching. It's really not. If we were to hook up a analog oscilloscope, it would just be very smooth as butter. But the oscilloscope kind of sputters and puts, and this is like one of the things this Handtech does, kind of annoying. All right, so anyway, I'm going to kind of tell you, I'm putting right now barely touching this thing. And now I'm pushing harder, I'm pushing quite hard, and you can see the voltage on the oscilloscope there is 4.4, and I'm not going to be able to get it to get all the way up because of that voltage divider, but I got it close, 4.6-ish volts all the way there. All right, so I mean, I had to press really, really hard to get it to there. Now, let's go ahead and let's change that RM resistor. So that RM resistor, and let's change what that scale is. So let's get our 10K, and it's always a challenge looking through everything. All right, so there's not a lot of power going on in here, so I'm just going to undo this in real time, and hopefully nothing will explode. All right, I'm not going to turn anything off. I'm just going to grab that 100K right out of there, and I've got a 10K. What's 10K? Brown, black, orange. What's the 100K? Brown, black, yellow, right? All right, let's hook this up, and this is just going to go back to ground. Ideally, if I can get my fingers in there. Okay, good. All right, so we got this back, we got this back. Okay, so everyone take a look at that oscilloscope. Now remember, if you remember the other chart, with the 100K, the voltage went all the way from 0 to 5, but it was extremely nonlinear. But with this one, we're going to have to apply a certain amount of force, then we're going to have a dynamic range only a couple volts, right? So watch. So now I'm applying a good amount of force. Now it's getting kind of linear. Now I'm pushing. I'm pushing really hard now. I mean super hard. I'm busting my finger. You can see my finger turning white. So we went up to 3 volts and 0 to 3. So you can see, remember, it's exactly what we said. You have a less dynamic range, but it's got a much linear range in here in that smaller dynamic range, right? So that's where we'd want to work this thing. So if this was a sensor and it was working in this force amount of force, which I'm feeling like is I don't know, a quarter pound, a couple pounds of force I'm pushing down here, this would be the resistor that we want to use. Okay, so that's that. Now let's do something else here. So let's first, I want to put that other resistor back because I like it going all the way to 5 volts, even if it's nonlinear. All right, now let's have some fun because that's what life is about. Let's add a LED. Let's add a LED. So we're going to take an LED here, and we're going to put the LED here, just like this, right at this output. And then we're just going to put a 100 ohm. I want to limit the current because I won't be able to pull that much current through that LED. So we'll put 100 ohm, and that'll limit the current so we don't mess up the op-amp. All right. Okay. So now this 100K is going to be irrelevant. It's not going to really affect the circuit. It's just there to keep the circuit kind of stable as we take things, connect things and disconnect things. Okay, so here we go. So now I'm going to go ahead and I'm going to apply force here. You can see on the oscilloscope, which is still there, that we've got 0 volts on the oscilloscope. So as I press this, it's going to go all the way up to 4.6 volts, and we should see that LED turn on in a nice, semi-linear fashion, as smooth as I can apply force. So I'm applying force. And you can see the LED getting bright, getting this bright. Woo, how cool is that? So I'm just kind of pulsing the force with my finger. It's not turning, there, and I can just control it. All right. Now, hey, So right now you do that and see it just kind of staying on there. Let's smooth that, right? So let's smooth that. Let's go ahead and let's put a 22 microfarad, which I just happen to have here. Let's put a 22 microfarad and let's make a filter, and this will charge. So this is basically going to it's going to charge each time, and it's going to slowly discharge, right? So we're going to put that right here at this node. If I can get it in here, let me see. What we'll do is we will go like this. Never enough room. We'll make some. There we go to ground. Okay. Now check it out. And then, hard to tell. Hard to tell. Yeah. It's discharging. It's also discharging into the OpAmp. So it's not having it's smoothing it a little bit. All right. Okay, so that's that. Now let's see. Okay, what was the other thing that I wanted to talk about? So for example, we've got this voltage here, right? And then what we could do is we could use another OpAmp, what's called a comparator, and then we could basically, when this voltage hits something, say like right there. So if you look at the oscilloscope, right there, it's 3 volts, right? So we could set a comparator, which is another analog device. It's based on op amps. Or you can make a comparator out of an op amp. And at 3 volts, it would snap on and turn its output on. So then we would basically have a threshold, and at 3 volts, which is some certain force, right? Then it would turn something on. Maybe it would say, hey, you know, the load is too much for the elevator, or whatever. All right. Now, the last thing that I want to show you is this. So we're sitting here and we're going, this is super cool. As I press on this thing, I get, you know, a voltage out of it, and I've got those charts in the data sheet. But I mean, I want to make this really accurate because I want to make a scale. I want to measure. I want to know exactly how much force you're applying here so I can convert it to a weight or whatever. How do you do that? So how do you measure that? Well, what you need is you need equipment, and you need equipment to measure this stuff. So let me show you a piece of equipment. This baby is my, basically it's a force sensing tool. Let me open it up here so you can see it. There it is. So there it is right there. So this and the power supply, and it's got a serial port so you can log onto the computer. So this is a piece of equipment, and what this equipment does, and it's got these different attachments here, so you can attach it onto the head so you can push things, pull things, poke things, do all kinds of things. So we are just going to use like this one. All right. All right. So I'm going to close this up and move this. And it's been a while since I've used this. So anyway, you basically attach this on here. And this guy is called the, it's the HF50. There's many, many models, HF50, HF500. This will do 50 newtons, I believe. All right. Okay, so now let's see here. And this thing is kind of upside down. All right, so I'm just gonna hold it here, and then I think you can see it. So let's go ahead, let's turn it on. All right, and I think you can see, yeah, that display is good. So the battery's been sitting in a box a while. All right, it's stabilized and it's calibrated itself. Now it's in newtons right now. Can you see that little N there? All right, so let's just put in something we're all a little bit more familiar with. Kilograms, pounds. All right, and kilograms are not force, kilograms are mass, right? But on a planet with gravity, you can say that they're a force based on the gravity. Okay, so we have the force sensor on here. All right, and then we're in LB mode here. Okay, so now let's go ahead and push against this. And as we push against this, see, we're getting a negative force, right? Because this direction just happens to be the negative direction. If I pull on it, we'll get a positive force. All right, so now, you know, again, it's like, you know, you think like a few pounds is not a lot, but it is. I mean, I'm pushing quite a bit right now. There's 3 pounds, there's 4 pounds, you know, 5 pounds with my thumb. And, you know, I can go more, 7, 8, 9, 10, and I just, you know, exceeded it. Same thing on pulling. So now what we can do is, okay, so let's put it back in Newton mode. All right, put it back in, does it have a scale? No, just Newton mode. All right, so now what we're going to do is this. So again, let's make sure we can read this. There's 3 newtons, negative 5, whatever. Okay, so I can push and pull, whatever. Now, let's take this back here. So now I'm going to show you the whole setup. So now what we got here is we got this. On the oscilloscope, we've got our voltage, so we can see our voltage, right? So I'm gonna push this over here, so we can kind of put everything. As a matter of fact, yeah, I'm gonna put this over here because I know that the oscilloscope is over there, and it's gonna kind of be occluded. Yeah, we'll put it up in the corner. That's what I'll do. Okay, so there we go. All right, so here we go. So now what I'm gonna do is I'm gonna push on this, And now, let me see that so you can see that number good. So we see the voltage moving on the oscilloscope. We see the force moving here. So then what you would do is you would basically test the test force. So there's 3.7 newtons, and there's the voltage for it. Then I let off. There's 1.5 newtons, and there's the voltage for it, and so forth. So we would actually calibrate this and manually do this, create a table. Now I'm sitting here with my fingers on this doing it, but we would put actual loads on it, and 1 newton, 2 newton, 3 newton, 4 newton, and you can actually get loads, pre-made weights of an exact weight, and then that way you could apply it here to create that curve, and then we know what our voltage is, and then that's how we create our lookup table, and we can create our perfect scale. All right, so that is using the force sensing resistor. Cool little device. You just need an op-amp, a couple parts. Maybe you want to calibrate it, or you can just kind of eyeball it and do it yourself and figure out what the forces are, but that's that. And that's all there is to it. Let's take a quick look. I just want to show you this right here in case you're interested in buying one of these. All right, so back here, let's go back here and let's go to, I already found this on Amazon. So if you just search for HF50 force meter, they'll start coming up here, and they're not cheap. 130, 115, so about $100, $150 to get one of these. And that's it. That's exactly what I just showed you. And then again, they have them. This one's a 500 Newton, mine is a 50 Newton. Now, the higher, so again, depending on the price, if it's 500 Newtons, it'll be less accurate. If it's 50 Newtons, it'll be more accurate, usually for the same amount of money. Or you can get a 500 Newton that's just as accurate as a 50 Newton, but it's going to be a little bit more. All right. So that is it for our force sensing resistor bonus lecture. So I hope that you like that, and you can use these sensors to make something cool. I don't know. To check, one thing might be cool is use the sensor on a little cat door, dog door. It opens up the door, closes the door, something like that. Or you could put one behind a wall and just push on a wall and no one would ever know, and it flips a switch or does something or turns a light on or closes a door, secret passageway. Anyway, so that's it. So I will see you in the next bonus lecture. Bye.